Hello, this is Sareem from Exam Hub Fab. Today I'll be solving Cambridge IGCSE Physics Paper 6 Alternative to Practical 0625, Paper 6, variant 2 February-March 2021. Question number 1. A student investigates the motion of an oscillating meter rule. He uses the apparatus shown in figure 1.1. Part A. The student ensures that the meter rule is horizontal. Briefly describe how to check that the meter rule is horizontal. You may draw a diagram or draw on figure 1.1 if it helps to explain your answer. So the question is asking you to make sure that this meter rule is parallel to this horizontal bench. What we can do is take measurements of height of the ruler at two different points, let's say from here and here. If they're equal, then we can conclude that meter rule is horizontal. Calculate the distance d between the threads. Okay, so distance d from previous diagram from figure 1.1 is distance between these two strands. Now, in this part, one strand is at 2 centimeters while the other one is at 98 centimeters. So distance d is going to be 98 minus 2, which is equals to 96 centimeters. Part C twists the meter rule a small amount as shown in figure 1.3 and then lets it go so that it oscillates in a rotation motion. He measures the time t for 5 complete oscillations of the meter rule, which is 3.63 seconds. Suggest why it is useful to take a trial reading for this experiment. Okay, so this kind of oscillation where you twist from middle and finding its oscillation time or time period is not as easy as that of a pendulum or spring, because here there are two ends of the scale that are going to oscillate at the same time and can cause confusion in your observation to find the value for time t. So a trial reading will help us in determining whether it is even possible to get the measurement out of this experiment. Part D, the student carries out the same procedure for d values of 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters, and 60 centimeters. Remember that distance d is the distance between the two strands on the scale. His readings are shown in table 1.1. For distance d, 20 centimeters, calculate and record in table 1.1 the value of 1 by t, where t is the time for one oscillation of the meter rule. Use the value of time t from table 1.1 and the equation 1 by t is equals to 5 by small t. Here capital T is the time period, means time taken for 1 complete oscillations, and small t is the time taken for 5 complete oscillations. So for the distance d, 20 centimeters, they're asking you to find the value for 1 by t. First of all, you need to find the value of capital T, which is going to be equals to small t by 5, since this is the time for 1 complete oscillation and this is the time for 5 complete oscillations. So small t in this case, where d is equals to 20 centimeters, is 17.85 divided by 5. Hence the value for capital T is 3.57 seconds, which means that 1 by t is going to be equals to 0.28 per second. And remember that your answer best be rounded to the same significant or decimal figures as others here in table 1.1. So your answer for 1 by t in this case, where d is equals to 20 centimeters, is 0.28 per second. Now part E, plot a graph of distance d on the y-axis against 1 by t on the x-axis. So let's start having our axes labeled first. So your y-axis is going to be distance d, and don't forget mentioning the units. And this is going to be 1 over time period, and this has a unit of per second. Now our d is going to range from 20 centimeters to 60. So let's start marking from 10 all the way up to 60 on our y-axis. So our y-axis is going to range from 10 to 60, and 1 by t is ranging according to table 1.1 from 0.28 to 0.88. So let's start from 0.1 all the way up to 0.9 on our x-axis. So this is our graph. I know it's not as perfect, but make sure yours is a straight line. Now remember that after labeling your axis, make sure that your plotting occupies at least half of this graph area or grid. Make crosses rather than dots because crosses will show precision in your graph. Part F, determine gradient G of the graph. Show clearly on the graph how you obtain the necessary information. So gradient of the graph, which is a straight line, it's going to be difference in two y values divided by difference in their respective x values. So let's suppose I take these two y values, which is at 30 and at 50. So I'm going to draw a triangle. And you must show this triangle. J is equals to y2 minus y1 divided by x2 minus x1. 50 minus 30 divided by 0.72 minus 0.44, which is equals to 71.43, since last values in the table are also corrected to 2 decimal places. So here, 2 decimal places. Part G1, explain why it is more accurate to measure the time for 5 oscillations rather than for 1 oscillation. Okay, so usually when we are to find the time period for some oscillations, we record time for more than 2 oscillations and then take average to get the value for capital T. But why do we do so? To reduce the percentage uncertainty of the timing errors. Part 2, describe how the experiment could be improved to make the readings more reliable. So to increase the reliability of your values, we can time several readings, then take their average. Question number 2, students investigate the cooling of hot water in 2 different cups. They use the apparatus shown in figure 2.1. Cup A is made from thin plastic. The top of cup A has an inside diameter of 7 cm. Cup B is made from expanded polystyrene. The top of cup B has an inside diameter of 8 cm. Part A1, record the room temperature shown on the thermometer in figure 2.1. So this is 20, this indicates 20 and this indicates 30, and there are 10 units in between. So each unit represents 1 degree Celsius, so 21, 22, and 23. So the room temperature that this figure 2.1 indicates is 23 degrees Celsius. Part 2, describe 1 precaution that you would take to ensure that temperature readings in the experiment are as accurate as possible. There are many ways to ensure the accuracy of temperature reading, but when reading a temperature scale, it's most important that your line of sight be in the direction which is perpendicular to the scale. Part B, a volume of 100 cm3 of hot water is poured into each cup, and the initial temperature theta is recorded in table 2.1. The temperature of the water in each cup is recorded every 30 seconds. The values are shown in table 2.1. Complete the headings in table 2.1. So T time interval, which is every 30 seconds. So this will be in seconds. Theta is temperature, which is going to be recorded in degrees Celsius. Part C, write a conclusion stating which cup, A or B, is the more effective in reducing the cooling rate of the hot water in this experiment. Justify your answer by reference to the results. So which one is better at insulation than the other, cup A or cup B? Now, temperature of cup A falls 2 degrees Celsius or more every 3 seconds for the first 90 seconds. In the first 30 seconds, it falls from 87.5 to 84.4, that's a fall of 2 degrees Celsius. Then 84.5 to 82 degrees Celsius, that's 2.5 degrees Celsius of difference. From 82 to 80.5, it's 1.5 degrees Celsius. And then from T is equals to 90 onwards, the difference becomes smaller from 80.5 to 79, which is equals to 1.5 again degrees Celsius, then 1 degree Celsius, and again 1 degree Celsius. But cup B's temperature doesn't fall at a greater rate. It first falls by 2 degrees Celsius, then 1.5 degrees Celsius, then again 1.5 degrees Celsius, and then at 1 degree Celsius from t is equals to 90 seconds, and 1 degree Celsius, then 1.5 degrees Celsius. So the fall in the temperature for cup B is at a much slower rate, so we can conclude that cup B is more effective in reducing the cooling rate. And we can give reference to the values that is in table 2.1 to support our statement. And the reference is going to be all around the difference in temperatures after every 30 seconds of interval. Part D1, calculate XA, the average cooling rate for cup A over the whole experiment. Use the readings for cup A from table 2.1 and the equation, where T is equals to 180 seconds and delta 0 and delta 180 are the temperatures at time T is equals to 0 and at time T is equals to 180 seconds. Include the unit for the cooling rate. So average cooling rate for cup A is equals to temperature at time T is equals to 0 for cup A, which is 87.5 degrees Celsius, minus temperature of cup A at T is equals to 180 seconds, which is 77 degrees Celsius, divided by capital T, which states over here that it is 180 seconds. So the average cooling rate for cup A is equals to 0.058, and this was in degrees Celsius while this was in seconds, so degrees Celsius per second. Part 2 suggests an additional experiment to show how the lid affects the cooling rate of cup A. Explain how to use the additional results to show the effect. So the additional experiment we can conduct to find whether cooling rate differs if we remove the lid from cup A, because in the last experiment we had lids on top of both cups, cup A and cup B. However, in this particular part of the question, we are only discussing cup A, and the results that we are going to use, how to show the effect out of those additional results. Now, we are going to calculate the new average cooling rate and subtract from the cooling rate that was of cup A with the lid on, to know whether the cooling rate was higher this time. If after subtracting it from the last cooling rate gives a positive value, that will mean that the cooling was faster with no lid on cup A. Part E, a student wishes to compare the effect of the materials of the cups on cooling rates. Suggest 2 variables that she should control to make this test fair. So she should first make sure that the initial temperature of both cups and at time t is equals to 0 is the same, and also keep the diameter of both cups the same, because the only thing that she wishes to compare is the type of material of the cups. So initial temperature of both cups need to be the same. Also, keep the diameter of both cups the same, which was different in the last few parts. Question number 3. A student investigates a resistor and a lamp connected in series. She uses the circuit shown in figure 3.1. Part A. The student moves the crocodile clip on the resistance wire so that the value of the potential difference across the lamp is 2.0 volts. She measures the current I for the lamp and resistor in series. She then connects the voltmeter to measure the potential difference VR across the resistor. Read and record in table 3.1 the values of I and voltage across resistor are shown on the meters in figure 3.2 and figure 3.3. So the current across the resistors and the lamp, since they are in series, will be the same, and it is this indicates 0.1, so this will be 0.18 amperes. So the current across the whole loop is 0.18 amperes. Now this is the potential difference across resistor. This mark indicates 2.5, as the PD across resistor is 3.7 volts. Part B, the student repeats the steps in Part 1 for values of 1 volt and 5 volt across lamp. Her readings are shown in Table 3.1. Calculate and record in Table 3.1 the resistance of the lamp for each value of its voltage. So resistance across lamp is going to be equal to the voltage across the lamp divided by the current that flows across the lamp. So RL is equals to VL, which is 2 volts divided by the current. So 2 divided by 0.18, this is equals to 11.1 ohms. Again, 1 volt divided by the current, which is 0.15, this is going to be equal to 6.67 ohms. 0.5 divided by 0.12, this is going to be equal to 4.17 ohms. Now, resistance across the resistor is going to be equal to the voltage across resistor divided by the current in the loop, since they are in series. So resistance across voltage across the resistor 3.7 divided by the current in the loop, which is 0.18. So 3.7 by 0.18, this is equals to 20.6 ohms. Voltage R3 divided by 0.15, this is equals to 20.0 ohms. 2.4 divided by 0.12, this is equals to 20.0 ohms. And we have to keep it rounded to 3 significant figures, all our answers. Part C1, describe the pattern of any change in the value of resistance across lamp as the voltage across lamp decreases. We can see that when voltage across lamp decreases, resistance across lamp decreases too, so they are directly proportional to each other. So we can write that RL decreases. Part 2, a student suggests that resistance of the resistor should be kept constant. State whether your results support the suggestion. Justify your answer by reference to values from Table 3.1. So the student wants resistor to have constant resistance, and here if you observe Table 3.1 values, resistance across resistor is about the same in all three cases, 20.6, 20.0, and 20.0. They are about the same values. So we can say that yes, the statement matches results and it is supported by values in this table within the limits of experimental accuracy. Part D, a student wishes to determine the resistance of the lamp when the potential difference across the lamp is 0.0 volts. Describe how the experiment can be extended to do this with the help of a suitable graph. So what we can do is, current stays constant no matter what you do to the voltage or resistance across the lamp. So we can plot a graph of resistance versus voltage. By obtaining more values, like maybe 3 or 4 values of VL, that's voltage across lamp, and then extend our line of graph to the resistance axis, because that's the axis you would like to read. So when you extend your line and it intersects with the y-axis, you will know that when voltage across lamp is 0.0 volts, what is the resistance? Part E, it is possible to use a variable resistor instead of a resistance wire to change the potential difference across the lamp. Complete the circuit in Figure 3.4 to show a variable resistor used for this purpose, the voltmeter connected to measure the potential difference across the resistor. Okay, so to change the PD across the lamp, we can connect a variable resistor in series with that lamp. And the question also demands that we need to measure the potential difference across the resistor. So a voltmeter will always be parallel to the component you wish to measure PD across. So a voltmeter across the resistor because we would like to measure the potential difference across the resistor. Question number 4. A student investigates the motion of a ball rolling down a slope. Plan an experiment which enables him to investigate how one factor affects the average speed of the ball. Average speed can be calculated using the equation, which is total distance traveled by time taken. The apparatus available includes balls of various sizes and materials. So we have balls of different kinds, a board which can act as a slope, blocks to support one end of the board. In your plan, you should state a factor which can be measured. So the question targets the factor that affects the average speed of the ball rolling down a slope. Now, what's that factor we have to deduce? Here they are giving us 1 unit of every apparatus except the balls that are of different sizes and materials. So diameter could be a factor in terms of size. So this factor that we are going to study in this question is going to be diameter of the balls. Diameter is that one factor that's going to affect the average speed of your ball, which is going to roll down the slope. Now, coming towards any additional apparatus needed in this question would be meter rule, which is going to be used for measuring the distance between the two fixed points that the ball will be traveling every time we record the values. So a meter rule. We'll give all the description down in the next page. I'll just mention all the apparatus here. And the second apparatus would be a stopwatch to measure the time for the ball's motion. Now, explain briefly how to carry out the experiment, including exactly which measurements are to be taken. Again, meter rule will be used to measure the distance, and stopwatch will be used as a timer to measure the time interval for which the ball travels between those two fixed points. And how we are going to carry the experiment, we are going to take several readings of time and distance for each ball to improve the accuracy of our readings, and then take average of speeds. State the key variables that need to be kept constant. One of the variables that need to be kept constant, I think, is the height at which your board should be placed. So height of the board. There are a lot of other things that need to be kept constant too, like type of board should be the same because of the friction of the board that needs to be the same every time your ball rolls down the slope, or the distance that the ball travels should also be kept the same. So this height of board is one of those examples. Draw a table or tables with column headings to show how to display the readings. You're not required to enter any readings in the table. So the quantities that we will be looking into would be the diameter, because that's the factor that we have to rely on. The diameter, so there are balls of different diameters. Distance is not that one quantity, is not among the quantities that we are going to include in this table, because the distance that is traveled by balls of all the various sizes is going to stay the same. So distance is not going to be among those quantities that we count here. Now, time taken is going to vary for all the for all the balls that are of various sizes and materials. So these are the two quantities that we are going to have in our table, and diameter will be in meters, whereas our time is going to be in seconds. Explain how to use the readings to reach a conclusion. You may draw a diagram if it helps to explain your plan. So I first should be drawing a diagram to make it easier or simpler for you guys to imagine how I'm going to carry out the experiment. One of the apparatus that they have given us is the blocks. So this is one of them, a blocks that's going to be placed vertically, and this slope will be leaning against it. This is a slope on which the ball is going to roll down to. And this is another block that's going to give support to the slope on the other hand. Now you must also not forget labeling. So this is the block, this is block 2, and this is the slope. Now the additional apparatus that we have are the meter rule, don't forget labeling, and we have the stopwatch too. And we have balls of various sizes. Or you could say we have balls of different diameters. Now coming towards the explanatory part. Now, how do we interpret this data and make conclusion out of it? We can say that with different diameters of balls, calculate the average speeds with all several types of balls, with all different diameters of balls, and then plot a graph to determine the relationship between the diameter of the ball and its average speed of rolling down the slope. If it's a straight line with a positive gradient, then that means that they are directly proportional, means when the diameter increases, the average speed of the ball rolling down the slope will be increasing too. And if it's a negative gradient, then the relationship will be inverse. So that was it. Thank you for watching.